Hey everyone, welcome back, and today let's solve Leetcode problem 2503 titled Maximum Number of Points from Grid Queries. Sorry. So we're given an n by n integer matrix grid and an array queries of size k, and we want to find an array answer of size k such that for each integer queries at index I, we start originally or initially in the top left cell of the matrix and repeat the following process. So if queries at index I is strictly greater than the value of the current cell that we're in, we get 1 point if it is our first time visiting this cell, and then we can move to any adjacent cell in either or all four directions, up, down, left, and right, kind of like the cardinal directions from that specific cell. Very importantly, we only get that point if it's the first time visiting that cell. So we can't just go in an infinite loop and keep getting infinite points by just going back to the two valid cells. It can only be the first time to get that point for that cell, assuming it's strictly greater than the value of the current cell for that query at index I, right? So if the cell doesn't meet that criteria, we don't get any points, and we simply end that process or that path, if you will. After the process, answer at index I is going to be the maximum number of points that we can get, and note that for each query, we're allowed to visit the same cell multiple times. We want to return the resulting array answer. Now, we're allowed to visit the same cell multiple times, but that does not mean we're going to get points for all the different times that we actually reach or touch that cell. Only the first time do we get a point for it. And again, we want to return the resulting array answer. Very importantly, note that it's going to have the same length as our input array queries, and for each query index is going to return or kind of output the maximum number of points that we can get starting from the topmost cell. So let's go ahead and look at the example that they also highlighted, kind of with the paths that we would take in each one of the three images for each one of the three queries in the input queries, right? So in this case, our grid is going to be a 3x3 grid where both m and n are equal to 3, and our queries are 5, 6, 2, right? In this case, we have an output of 5, 8, 1. And what these numbers, or 5, 8, 1, really signifies is it's basically telling us that the query indices are 5, 8, and 1. Those are kind of like the values of the cell value that we should be looking out for. Because again, for 5, assuming we're on the first or 0th index of the input array query, 5, if it's strictly greater than the value of the current cell that we're iterating over, then we can get 1 point. If any cells are less than that value 5, then we can't get that point, and so we have to just continue our path or end the process. In this case, the reason why our output is 581 for the queries to be 562, because, well, let's go ahead and look at the pathways that they kind of highlighted for us. In example 1, right, they show, okay, this is for the 5 query, right? The diagrams go above, again, show which cells we visit to get the points for each query. Notice how, again, we want if queries at index I to be strictly greater than the value of the current cell that we're in, meaning our current cell should be smaller than the query at that index, right? So we start from the top leftmost cell 1, and in this case, our initial kind of 0th index query is going to be 5. Notice how all of these cells in this pathway, they actually have a cell value that's less than 5. 1 is less than 5, 2 is less than 5, 3 is less than 5, 2 is less than 5, and so is 3 less than 5. Notice how we iterated over or explored 5 cells with that property in that path, and so quite self-explanatorily, the output for that specific index query, 5, is also going to be 5 because there are 5 cells in this path that we took that actually did have a cell value or value just in general less than 5. And again, it cannot be equal to, it has to be strictly less than. So in the second query, we have 8. In this case, every single cell we can actually visit is going to be less than 8, right? We can go from 1 to 2, or rather, sorry, we have 6, right? In this case, all the cells, or every single cell in the entire grid, is going to be less than 6, except for this 7. So we can go over 1, 2, 3, 2, 5, 3, 5, 1. Notice how all of those cell values are less than 6, but 7 isn't, and so we can't iterate over that, giving us a total number of cells of 8, and so that's why 8 is going to be the output for that 6-cell query. And finally, for queries to be equal to 2, in that case, there is actually only one cell in the input grid that we can take a path over that actually does have a cell value less than 2, and in this case it's this singular one cell right here where we're initially placed, and that's perfect for us because at least we can grab that cell. We can't continue on the path because none of the other 4 directionally adjacent cells are actually strictly less than 2, and so we only have one potential cell for that query or that cell value 2, and so we have 1 for our output. So Just to quickly gloss over the second example here, in this case our grid is going to be a 3 by 2 or 2 by 3, always mix them up, and queries in this case is going to be just a singular cell value of 3. In this case we have an output of 0. We're starting at the initially topmost left cell, and we can't even do anything from here, right? Because we know our query is 3. 5 automatically is not even less than 3. It's literally greater than 3, and so we already break the rules from where we start, and so we can't make any moves. We can't do anything. We have to immediately end the process, and so we have an output of 0, because 0 cells can actually make a pathway to be less than that query or cell value 3, because we start at an invalid cell in the top leftmost cell value. So for the constraint series that M and N are going to be the length of the grid, more specifically the number of rows and columns in the grid, and they're both going to be between 2 and 1000, and the product of those two numbers, i.e. the number of cells we have, is going to be between 4 and 10 to the 5th power. K is going to be denoted as the length of the input array queries, and that length is going to be within 1 and 10 to the 4th power, and any value in the queries and grid cells are going to be between 1 and 10 to the 6th power. And that leads us to the main observation to now we can really solve this problem efficiently, which leads us to how do we solve it efficiently, right? Now we're actually going to solve this problem in the most efficient manner. We're actually going to be using something called the offline processing approach, and we're also going to be using a very common data structure, the priority queue. In this case, we want a min heap, and we're also going to have a BFS algorithm kind of structure in this solution, right? Min heap, again, its whole purpose is to kind of prioritize, hence it's called priority queue, prioritize the minimum values or smaller values, and so it's always sorted from small, or rather it always has the smallest value at the topmost kind of node of that data structure, right? So whenever I pop from a min heap, I'm always going to get the smallest value in that min heap, right? Now, that's kind of the data structures and algorithm that we're going to be using. How are we going to actually structure them in our actual deployment, in our actual solution? So again, we talked about offline processing, right? We know since each query is actually independent, and again, the order doesn't affect the result. We can answer these queries in any order we'd like, right? And so that's not going to actually directly affect our results. And so what we can really do to make it a lot more efficient and easier to manage is actually, believe it or not, sort those queries in ascending order. If we sort it in ascending order, we can then process them sequentially from smallest to greatest, or in ascending order, which is going to be a lot easier to kind of tell, because those in that ascending order, cells would depend on each other, right? We can build upon the previous computations, and we can also further, again, optimize that traversal for our BFS. And where is that kind of min heap priority queue going to come into play? Well, we always want to expand the least value unvisited cell, because of course we want the smallest possible cells on our path for all the queries, because we want all of our cells in our path to be less than each query value, and so we want to prioritize smaller cell values to kind of have a larger number of points or cells that we can collect for each query, right? And that's why we're going to have an actually usage of a min heap, right? We can always explore the cells in increasing order of their values, and that, again, that's also going to align with these sorted queries. Now, where are we going to kind of sprinkle in the BFS approach from this? Well, we know we're starting from the top left cell. How do we know that? Well, because the problem tells us so, right? We're initially placed at the top left cell of the matrix, and we want to repeat these operations, or we want to repeat this process, right? We're starting from the top left cell, and we can kind of just build our way from there with the 4 directionally adjacent cells BFS, right? So basically perform that BFS to actually explore all the reachable cells, i.e. the 4 cardinal direction adjacent cells, with those values that have less than the current query value, right? The current query value or index that we're currently processing. And it always makes sure that we always explore all the possible paths in that kind of ascending and systematic order. And again, we don't really want to kind of keep, revisiting. We don't want to always just keep visiting already visited cells. They're not going to give us extra points, like the problem also confirmed to us. And so we want to actually track which cells we've visited, right? And to do that, well, there's a very, very simple data structure. It's called a set, a visited set, right? Basically, we want to actually avoid revisiting those cells, and we only want to ensure that each cell is counted only once per query to also further optimize our runtime. And so, of course, we're going to have a maintained visited data structure. I may have said set. I think for this problem, a matrix might be a little easier looking back at this now. So we probably will have a matrix, but more of that later. That's kind of the whole purpose of that visited data structure, right? So now let's go ahead and actually get into the main kind of deployment and code for this solution. So, like I usually do this for most matrix problems. I think it's just a lot easier for me to iterate over it and access these corresponding integer values. And so I get the number of rows and columns and store them in the integers m and n. So like the problem told us, length of grid is going to be equal to m, the number of rows, and length of grid at index 0 is the number of columns stored in the n value, right? Really, this is really just to kind of store the number of rows and columns, and really just to help us iterate over the array and build our visited matrix in a more kind of efficient and easy manner without having like too hefty and complex lines of code, at least relatively. Now, we want to actually get our index queries, and this also aligns again with that kind of sorting the queries property, right? We want to kind of sort those the queries with their index and value because, of course, we want to go in ascending order to manage all the queries a lot easier because they depend on each other, like we see in these problems constraints of each cell being strictly greater than the previous values. So I'm going to initialize it to be index query and give you a minute as I type it out. It's going to be the sorted, right? Sorted is actually a built-in method in Python, and in this case, it's going to be a tuple of length 2 for each value or kind of index in the queries array. So it's going to be the actual value itself, and it's going to be also mapping or kind of in the same tuple with its corresponding index. Now, how do we get the index along with every value in an input array or iterable? Well, we do that by enumerating in Python. So it's going to be every index, value, and index. Again, this is kind of list comprehension here in Python for every index and value. And again, the enumerate, because we want to enumerate over the list, not just loop over it regularly, of the queries. Right, again, this is called list comprehension here. Again, we're basically just creating a list of tuples, each of length 2, corresponding or having a query value in its original index, right? Then we actually sort it because we want to sort it to get all the query values in ascending order, right? And why do we actually want to sort it? Well, because it actually helps in processing the smallest queries first, which is also very important for the efficiency of our approach, because we want these small values to go first, as they kind of are the harder values and more weaker values, if you will, to really go over, right? So once we get the index queries, now let's actually initialize our answer list. This is effectively what we're going to be returning. This is going to be of that same length queries with the corresponding maximum number of points or cells we can visit for each query index. So of course it's going to have the same length of the input array queries. And I'm just going to actually initialize it with all zeros, kind of like a filler placeholder value, right? Again, it's going to basically just store the result or maximum number of points that corresponds to each query, and it's going to have, very importantly, the same length as the queries list because it will have one answer, i.e. the number of points or maximum number of points for one query, right? You see that kind of relation there, right? Now, once we actually get that, now let's actually initialize our min heap, right? It's going to be basically still with brackets, and I think it's just called straight brackets like we see in lists as well, and it's going to start off with the topmost cell. Why is it starting off with the topmost cell? Because the problem tells us that that we're initially placed in the topmost cell, and so it would make a lot of sense to start in that topmost cell. It's going to be the topmost cell and the two kind of row and column values, 0 and 0. I think it's easier if I don't space them out too much. I think that should be good though. Anyways, yeah, so again, this minimum heap, what is it really doing? It's, again, notice how I still put this in parentheses, meaning it's still a tuple of length 2. Is going to have the value of the top left cell and its actual coordinates or row and column values 0, 0. So the value of the top left cell, grid is 0, 0, and the row and column or index values 0, 0, right? And what is the main kind of priority or that was a pun? I mean, what is the main kind of goal of this priority heap or this min heap priority queue? Well, it's always going to help us process the cell with the smallest value first, because that's what we're trying to prioritize to get the most number of or maximum number of points, because we want all of our cells to be as small as possible, to be smaller than the current cell or query that we're processing, right? And a very good way to do that is based on the min heap, because again, the smallest value is always going to be the topmost value that we pop off directly from the minimum heap. Right, so now let's actually initialize our visited array, kind of keeping track of which cells we visited in which paths. And so I'm actually going to make this a matrix here. It's going to be initialized to all false because, of course, initially we don't iterate through any matrices, times n for every single value in the range of m. So it is going to be two-dimensional, as you see with this kind of nested comprehension, I believe it's called, right? Basically, it's going to have the same dimensions as a grid, m by n, right? And effectively, it's going to track which cells in the grid we actually visited, right? It's more specifically whether we visited a specific cell during the BFS algorithm. Now, what's the first thing that we should do, kind of like the base case of this visited set? Well, we immediately want to mark 0, 0 to be true. Why do we want to do that? Well, again, we start at the top left cell, and the top left cell has a coordinate of nothing but 0, 0. And so since we're always starting at that for each kind of beginning of each iteration or BFS call, we always mark that as true because, of course, we know that we're always going to start or we've always added it to the heap. We're always going to start with that cell and go on with 4 directionally adjacent cells from there, kind of building off our path for all the values that are less than that current query value that we're processing. Now, again, the next line that I'm going to have, you won't really need it. I think you can kind of push it into an iteration kind of to make your code a little bit concise, but I like to have it because it's a little bit more easier to see and it's a little bit more simple in my opinion. I like to usually initialize a directions array, right? This is basically all the different 4 cardinal directions or 4 directionally adjacent cells that we can move on to, again, i.e. up, down, left, right. You don't need to have this, but I usually have this just for best practice and just really for me, right? So what are the different directions we can go? Kind of more specifically, the offsets from the current cell will be -1, 0. It'd be, of course, 1, 0, or it could be 0, -1, or even a 0, 1. Again, these are just the offsets for going up, down, left, or right from the current cell, right? Because we want to actually explore those 4 possible movements to explore those neighboring cells. And that's the whole point and use case of this directions array. Now let's actually finally initialize our last integer that we're going to be using. It's going to be the number of points we have for each cell or query, right? It's going to be keeping track of the number of unique cells that we visit through each query and that have a cell value less than that query, right? And of course, initially it's going to be set to 0 because we really haven't iterated through any cells in the grid yet. We haven't done anything yet. This is all kind of like the pre-initialization before we're actually processing the input. Once we initialize all of these integers and data structures and whatnot, now let's begin our main BFS kind of a traversal and our processing of the query or of the input as well. So let's actually use this with a very simple for loop here. For every single query value is what I'll call it, and query, you guessed it, index. Every index and value is going to be, of course, mapped or corresponding to each other in the indexed queries. I believe it's what I called it. Yes. And again, the index queries is nothing but the sorted version of the queries, actually to get all of the query values sorted based on ascending order to get the smaller query values earlier, right? Again, we want to process those queries in ascending order to build upon the previous results a lot more efficiently because, again, they depend on each other in these smaller cell values requiring less cells in their path. Right, so while that's the case, while the min heap is non-null, meaning while we actually have nodes or cells to process, and min heap in the topmost node, how do we get the topmost node? It would basically just be 0, 0 at index 0, 0 that is, while that's less than the current query value, meaning while it's still an actual valid cell, right? So while we still have a non-empty set and the smallest value in the heap is still less than the current query value, so while we're still only considering cells that can contribute to the current query's result, well, let's first pop off that current value and xy coordinate. So we'll get the current value, and we'll get the x and y coordinate of the current cell. It'd be x and y, and I believe this is called unpacking in Python. It's going to be heap q dot heap pop, right? And again, heap q, okay. And again, for our parameter, well, we want to actually pass in the data structure or the minimum heap that we're popping from. And in this case, I really just called it min heap, and so I'll really just pass in the min heap data structure name, right? We're actually popping off that cell with the smallest value from the min heap and also retrieving its value in coordinates x, y. And we know that it's still valid because we're still in this while loop here, meaning it's still a valid cell that has a cell value less than the current query value. So while that's the case, let's actually increment the number of points by 1. Because guess what? Since this is valid and we just popped it off from our minimum heap, i.e. we're using it, well, we just collected it. Meaning in this path, we just use it one more time, and so the points for this query value also has to be increased by 1, right? Because the cell does satisfy the query condition of having a value less than the query value, so we have to actually increment the points counter for this query index. Again, that's going to keep track of how many unique cells or points we can actually visit for the current query. Now, once we actually get the number of points in the current cell, now let's actually go through this new cell's 4 directionally adjacent cells and keep building on from there. And the way we can do that is using our dictionaries input, or rather dictionaries array or tuples that we initialize on line 9. So for every dx is what I like to call it in dy, kind of like offset directions of the 4 possible movements to explore them up, down, left, and right from the current cell xy. That's the whole reason why we actually got the coordinates xy in the directions array. We'll get the new x coordinate and the new y coordinate to be x plus the dx offset and y plus the dy offset. Again, the whole point of why we got those x and y coordinates was to do this and actually efficiently explore all the 4 directionally adjacent cells from the current cell that has a coordinate value of x comma y, right? We're actually adding the respective direction offsets dx dy to each of the current coordinates x, y to move to a neighboring cell for each direction, right? As we iterate over the directions input or array that we initialize on line 9, right? Now we have to actually check is this new coordinate within the grid boundary still, meaning it's actually not like an out of bounds index and it hasn't been visited before, right? And it's going to be pretty lengthy, but I'll explain how it goes. It's pretty self-explanatory. If nx is still within bounds in the input, meaning it's at least 0, but less than the number of rows we have, or rather, sorry, that should be m, I believe. And the same logic should be applicable for ny, but in this case, it should be for the number of columns we have, so n, and we haven't visited this new cell nx and y, meaning it should be false. False meaning we haven't visited yet. So again, we're checking if is the current new coordinate of the new cell nx and y, is it within the grid boundaries, and have we not visited before? If both of those conditions are true, then we can actually continue the process, and it's still a valid process and cell to continue, and we can keep moving forward. And so if that still is the case, well, great. Let's use this cell as well. So we'll mark it as true because, of course, we just saw it. We just visited it. So now it's true in this current pathway. And we also then want to get it in our heap Q. So heap Q dot heap push onto the min heap. That's the first parameter that we're going to be having, the actual data structure that we want to push new value onto. And we then actually want to push the new value along with its corresponding coordinates. Keep in mind, that's very important because we build off this value in future iterations of query indices. So grid at nx and y and the actual coordinates of this data structure or of this cell. And what is that? Well, that's basically literally just nx and y, the coordinates of this new cell. We're pushing the new cell's value and its coordinates nx and y and grid at nx and y to the minimum heap to ensure that the next cell that we process is still always going to have the smallest value, but we also maintain the order that we need for the efficient traversal while keeping track of those extra 4 directionally adjacent cells that we process. And then while this is still true, we also, or once we actually exit that while loop here, for every iteration of this while loop here, rather of this query index, once we're done with this while loop here, but still in the for loop, we then want to get the answer and update that. Once we actually fully build this query, we then want to update it in the resulting answer list. So answer at this new query index, that's a query index for the current query that we just processed in this while loop here in this iteration, is going to be, guess it, you guessed it, the number of points that we had, right? It's literally just going to be the number of points that we built, number of cells that we actually traversed for this current query cell, right? That's going to always ensure that our final output in the order, or rather is going to be in the same order as our input queries. And effectively, what's the last thing we do once this for loop is actually done executing, once it terminates? We then want to return our answer array because it would be fully built. It would actually have the correct maximum number of points or number of cells visited for each query, having the same length as our input array queries. So unless I made it in the syntax 0, 0, there should be accepted and there should be a valid solution. Okay, let's go ahead and see what I did wrong here. Indexed. Okay, sorry. Now this should work unless I made a silly little syntax or logic error here. Let's go ahead and double check. Okay, yeah, so there should be heap Q, not he Q. Sorry about that, guys. Okay, oh, oops, looks like I forgot a parentheses. Sorry about that. And I probably made another very, very simple error here. Let's go ahead and double check that. Yeah, okay. Oh yeah, sorry. Looks like I forgot another parentheses. Sorry about that, guys. Let's go ahead and see what else I did wrong here. But anyways, as you can see, this is actually the most efficient solution. It does get accepted on Leetcode. It is just about as efficient as you can get it to be. And notice how, just a quick thing that I kind of forgot to gloss over, the reason why we sorted the query values in ascending order is because we built off of them. They kind of depended on each other, and we built off of them in each iteration as we iterated over the queries, right? We never actually reset the points back to 0 because we know that any cell values that work for a query that's small will also work for a query that's larger. Let's go back and look, kind of logically break that down. We know 5. We know all these cells 1, 2, 3, 1, 2, 3, and then these 2, 3 cells. They're going to work for 5. notice how 6 is greater than 5. And so if all of these cells work for 5, they should 100% work for 6, because 6 is greater than 5 and they're all less than 5. And so if they're all less than 5, they all have to be less than 6, because 6 is greater than 5. And so it's much easier to do that instead of actually resetting the points each time, because we know that we're always going to be processing queries in ascending order. So we don't have to kind of reset. We can just build off of the previous computations of previous query values. That's the whole point of why we actually sorted, right? So kind of an overall explanation of the code real quick before the video gets too long here. Basically, again, we're processing the queries in the ascending order after sorting them, only expanding that BFS when a new query actually needs it. And the BFS is kind of driven, you could say, by that min heap priority queue, where we're efficiently finding the maximum number of cells that can be visited under each query. And each query value, that is. And the result for each query is stored with its corresponding index in the answer, and that would also make sure that this is the most efficient solution. So for the runtime complexity here, to actually sort the queries, it's going to be big O of k log k, and for the actual BFS traversal, it's going to be big O of mn times the log of mn. Again, mn is just the number of cells we have in a grid, the dimensions of the array. Because of course each cell is actually processed once, and we push it onto the heap at least once, and the heap pop would still run in log time, and so overall the runtime complexity is quite kind of crazy. Kind of just to say that real quick, it's big O of m times n plus k, and that's multiplied by the log of m times n. And for these constraints here, it is, as you can see, still the most efficient solution. It may not sound very efficient with all the different, multiplication symbols and whatnot, but it is still a very efficient solution because, again, logarithmic time complexities are always a lot more efficient than you think. A great example of that is, of course, the binary search algorithm. So anyways, if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Sorry if the video took too long. See you guys in the next video. Bye-bye.